But the story is not about simplicity of that. The interesting thing is when you look at the same problem from different perspectives. So the next perspective I would like to take would be geometry, because this is algebraic. Never thought about it in geometry or physics. So let's do geometry. And here is the unusual geometric interpretation that I never used before. I would like to interpret this system geometrically. So what is it that I can do? I can look at all these values of y together, making a vector. And that is going to be a vector in n-dimensional Euclidean space. Well, that's okay. So you have a vector y in n-dimensional, high-dimensional Euclidean space. And that vector is given. You know all the components, all the coordinates of that vector. And then what? Then you subtract. What do you do? Well, why don't we put all the axes together, also making a vector. So you have a vector x there. And then what does it mean that you multiply each component by the same number m? Well, that means you multiply the whole vector by that number. So this is a number times a vector. And then, well, what do I do with this? All those b's that I have to subtract. Well, that looks like the same number b multiplied by a vector. What kind of vector? What are the coordinates of the vector? One, right? So I can think about a vector made by ones. All the coordinates are ones, but the vector is in n-dimensional Euclidean space. So now I have interpreted this left-hand side. And what is it that I want about this as a vector? Well, I know this is now equal to that vector made of errors. Let's call it E. And what am I asking for? Well, in terms of that vector E. Minimum value of what? Sum of squares, yes. What is it in terms of the vector? Is there a new word describing sum of squares of all the coordinates? Isn't it? The magnitude of that vector? So we want the magnitude of that vector to be the smallest. And now we have a complete interpretation in geometry of the question. But now we can think geometrically. Now how can we possibly think geometrically? Well, yes, the scary thing is that all these vectors belong to high-dimensional, n-dimensional Euclidean space. And that dimension can be thousands. So the good thing is that we have to deal with vector y, vector x, vector 1, and their combinations only. So these are all the vectors we have to draw, essentially. So let's draw a vector y. Because three vectors I can draw in 3 space. So vector y, vector x, and vector 1. And then what is it that we do? Well, what we do is we multiply x, that vector, by some number. So that amounts to making x maybe longer. So this is m times x. And I can draw that on the same line as x, right? I don't need extra dimensions to draw that. What else? Well, I can multiply 1 by b, just by making it longer, or shorter, or even changing direction. So just for simplicity, let's make it longer a little bit, and pretend this is a number b times 1. And then what? Then I take the sum of these two, and that sum is what I have to subtract from y. So let me figure out that sum. So this is the sum. And finally, what does it mean to subtract these two vectors? Can I draw the difference? I have this positive and that negative. That negative means going here. Right? So this sum, the difference is going to be going from this point all the way to that point. So the difference geometrically is this vector. So this is the vector E. So you see, the whole picture can be done in 3 space, because we will use only those 3 directions in that high dimensional space. And everything can be understood in this 3 space. So what is it that we are looking for? What is it that we want? We want this vector to be the shortest. Right? What are the limitations? Why cannot we make it 0? Well, it must end at this fixed point, because y is a fixed vector. Right? Where should it begin? What are limitations that we have on the beginning of this? Does it begin somewhere in that plane determined by the given 2 vectors, 1 and x? So it begins in that plane, but it ends somewhere. And of course, if this point is in that plane, that's great. We can make it 0. But by the random nature of x and y, you can guess it's not there. So you have to think about a point in 3 space and the plane, and the point is not on the plane, and what you want is the shortest vector from the plane to that point. Haven't we looked at this kind of problem? So we have to minimize the distance from the tip of y to the plane on the vectors x and 1. And that is very geometric condition. And what is the solution? was going to be the vector that minimizes the distance from the point to the plane.
Normal vector.
The vector perpendicular to the plane. So geometry suggests that vector E must be perpendicular to the plane. That's it. That's the complete geometric answer.